All right, we'll look at notes today for section 9.1. There's a lot of vocabulary for 9.1, so we're going to talk about the words that we're going to be using throughout the rest of the chapter here, and then apply those to some situations. As I mentioned in class, we're looking at our goal is to build up to be able to multiply polynomials together. These things called polynomials we'll talk about in a second, as well as we'll eventually be able to unmultiply them or factor them. It's kind of the end result of this chapter. So we'll start here with monomial. Mono, the prefix meaning one. So this is going to be one term composed of constants and or variables multiplied together. Examples of monomials are things we see a lot. So like any number, whether it be a fraction, is a monomial. Whether it be a whole number, variable, b, I guess, x, or we could combine these things. So like 3y to the third power, 6ab squared, so on. All single terms connected just by multiplication. Poly means many. So a polynomial is any time we take these monomials and connect them together with adding or subtracting. So one or many monomials connected by addition or subtraction. Okay, examples which we've see a lot. How about like x plus 3 is an example of a polynomial. Or how about 6x squared plus 3x plus 1. Okay. We'll talk about specific kinds of polynomials. Like a monomial is a one term. We have terminology for a two term polynomial. That's called a binomial. Bi like bicycle, binomial. Our first example here would be a binomial. We also have three-term polynomials, and those are called trinomials. This is three terms. Our second example here would be a trinomial. Okay, so one terms, two terms, three terms, and then in general, all these things are called polynomials, and if you have more than three terms, then we'll just call that general thing a polynomial as well. Okay. All polynomials have what's called a degree and a leading coefficient. And in order to find those, we're going to write our polynomials in what's called standard form, so we'll start here. Standard form is when we rewrite a polynomial such that the powers of the variables are in descending order. That's largest power to smallest power. When I use the word power, I'm talking about exponents. So we're looking at the exponents of the variables, and we're going to rearrange them in whatever polynomial is. We're going to rearrange them so that the one with the largest exponents first, the smallest ones last, and they're all in order in between. So for example, if I take my first polynomial here, I could start by changing this subtraction to plus negative, and now we'll reorder this so that the highest exponent comes first, namely this negative 2y squared comes first, then the 5y to the first power, and then this 9 with no y's, or y to the 0 power. This is called standard form. Okay. What's nice about if we're writing in standard form, then finding the degree and the leading coefficient of these polynomials is very easy. The degree of a polynomial is the largest, for our case, when we have one variable, it's the largest exponent associated with a variable. The largest exponent attached to a variable. Later on, when you take Algebra 2, when we start incorporating multiple variables, we'll see that degree is adjusted so that it's the sum of the exponents of all the variables. So if you have more than one, then we add up all the exponents that we see for any one term. What's nice is that since we wrote it in standard form, the largest exponent had to come first. So we can look at our first term in standard form and identify that the exponent must be the degree. So in this case, our polynomial here has a degree of 2. The leading coefficient is the coefficient or the number multiplied to a variable that leads our polynomial, or it's the coefficient. Coefficients being numbers that are multiplied to a variable. The coefficient that comes first when the polynomial is written in standard form. It leads. The leading coefficient leads. So the leading coefficient, abbreviated LC, the first coefficient that I see is this one. So the leading coefficient in our case here is -2. Okay, I'm going to quickly do this next two. The next three. Standard form would be -4b to the 4th plus 3b to the 3rd plus b squared. The degree in this case is the largest exponent associated with this b, which is 4. The leading coefficient is the number multiplied to a leading term, which is -4. Okay, standard form, 4y to the 6th plus 14y squared plus 2y minus 10. Degree in this case, the exponent associated here is 6. The leading coefficient is 4. Standard form, plus negative, negative 5x to the 5th minus 3x to the 3rd plus 2x squared. Degree is 5, leading coefficient -5. Moving on to the backside. To be a polynomial, expression must satisfy the following criteria. First, I'm going to give you in these 3 boxes, I'm going to give you a list of things that we don't want to see. Polynomials are nice because they look normal, they look plain, they look inviting, they don't look intimidating. There's nothing weird going on. So I'm going to list 3 things that automatically rule out polynomial. First, there can be no variables in a denominator, which, to recall, is the bottom half of a fraction. So examples of this might be 1 over x, the variables in the denominator. Another way to be sneaky and try to trick you would be to do something like this. Use a negative exponent, because from last chapter, in chapter 8, we discovered that negative exponents mean flip and make the exponent positive. So this is like a covert way, a secret way to turn a variable that looks like it might be a polynomial into something that's not. Okay, both of these are examples of not polynomials. Another is there can be no variables under a radical. A radical is a square root. And for our purposes, radicals you've already seen are square roots. So, for example, square root of x would be an example of a not polynomial. The last one are equations that we saw last chapter. So we also can have no variables in exponents. These functions are called exponential functions, which is what we studied in chapter 8. Those are not polynomials. Polynomials, so for example, if I did something like this is not a polynomial because the variable is in the exponent. Okay? There's a very good chance if our expression satisfies these three criteria, we're probably going to be a polynomial. It's highly likely going to fit. Okay, so we'll use this type criteria to test whether or not we have a polynomial. So, for example, if I ask you to tell whether the expression is a polynomial, if it is, we're going to cross off find this degree. If we've already done that. So if it is a polynomial, classify it by its number of terms: monomial, binomial, trinomial, polynomial. If it's not, then give a quick explanation of why it's not. So for instance here, this looks pretty normal. There's nothing weird going on. There's no variables in the denominator, no radical symbols, and there's no variables in exponents. This is a polynomial. More specifically, this is a monomial. Okay. Second one is not a polynomial. The reason for that is if I rewrite this, it's the same as 3 times a to the negative 5, which is 3 times 1 over a to the positive 5, variable in the denominator. Or negative exponent means variable in a denominator. This one looks good. Pretty normal looking. There's 3 terms, so this is a trinomial. Nine over m, well, it's just like this first one here. This is no variable in a denominator. Note that this contrasts with, if I made another example here, m over 9. This is a polynomial. The reason for this is m over 9 is the same as 1 times m over 9, which is 1 over 9, just a fraction times m. This is just some number times m. There's variables not in the denominator, variables not in a square root, variables not in an exponent. In fact, this is a monomial. Okay, this might be a good example these two might be a good example to kind of highlight or star in your own notes, as kind of contrasting things that look very similar but have very different answers. On the last one, yes, again, no radicals, no exponent variables, and no variables under a fraction bar. Yes, and this is a binomial. Last but not least, the last thing we do in our first section here is add or subtract polynomials, which is the same as combining like terms, which you've done quite a bit in your math careers thus far. So the last piece is something you already know how to do. It's just combining like terms. So we're going to go through and identify all the terms that have the exact same variable with the exact same exponents, and we'll add or subtract them together by adding or subtracting their coefficients and keeping the exponents themselves, the exponents and the variables the same. So for example, I'll do 3x, I'll find the like things, and I'll even do an extra step here and I'll just kind of regroup them. So I have minus, I'll do plus negative here, minus x to the third plus x to the third. Let's see, another thing I like would be 2x squareds plus 3x squareds. Notice I'm crossing them off as I go so I don't reuse them. Plus, let's see, I have a 3x, and I have a minus 12. Notice I wrote these in parentheses because those are the like terms. They have the same variable, the same exponent. So I'll combine here. Negative x to the third plus x to the third. That's like negative 1 plus 1 is nothing. This is 0. This is 1x squareds. And then these two, they have nothing in common. So 0 plus 1x squared plus 3x plus minus 12, or maybe we'll clean this up just a bit. X squared plus 3x minus 12. Same game down below, same game over here. Notice I did it and I found the largest part of x first. That way my answer is already in standard form. I have 4x to the third plus x to the third plus 2x squared minus 3x squared plus x minus 4, 5x to the third minus 1x squared plus x minus 4. When we subtract, this is how I subtract. Instead of subtracting, you plus negative 1 times all this stuff, and I distribute a negative 1. I can't stress enough that you should do this. Distribute the negative 1. If you choose not to, life's going to be a pain for you because you'll miss negative signs in here. So distribute this negative 1, and we'll start by rewriting it. So now we have 2c squared minus 8 plus 3 minus 3c squared plus 4c minus 1. And now we can play the same game we just did. Now we've turned the subtraction to an addition problem. We get, if I add an extra step here, 2c squared plus negative 3c squared plus 4c plus negative 8 minus 1, negative 1c squared plus 4c minus 9, or plus negative 9. Same game, subtraction in between, plus negative 1, and I'll distribute, and I get 5y squared plus 2y minus 4 plus y squared minus 4y plus negative 4y plus 3. So like terms would be 5y and y squared is 6y squared. We have a 2y and a negative 4y is negative 2y's. Negative 4 plus 3 is negative 1. And those are your notes for section 9.1.